So I started to give you a derivation, and then I realized I want to be here for this. I don't want to miss this. So, plus it's too hard to explain on a video. It's better for me to be here. So, we'll define that equation later. But what I'd like to do now is I'd like to just briefly, so that you get a sense of how to use this, because after this you should be able to do the first two sections of your syllabus. I'd like to go get out your textbooks, and we're going to turn to page 317, and we're going to try and do number 9. And we're only going to do part A, because the rest of it's just sort of rehashing the point, but we're just going to do part A. So part A says we've got a 0.6 kilogram mass at the end of a spring. And it's vibrating 3 times per second. So 3 times per second, that's a frequency. So 3.0 inverse seconds, or hertz, or whatever you want to say. So, and the mass is 0.60 kilograms. And it has an amplitude, which we're going to call capital A, of 0.10 meters. Sorry, 0.13 meters. I'm reading the wrong part of the problem. And the question in part A is, what's the velocity at the equilibrium point? Okay. Well, let's think about this. When the spring is squished, or at its maximum amplitude, right, what kind of energy does it have? Well, when it's at its maximum amplitude, it's sort of going back and forth here, right? But at either end, it's stationary for a split second. So we're going to say at the beginning it's got no velocity, so that means that it also has no kinetic energy. So if I do a conservation of energy equation, I can say that at the beginning I have no kinetic, it's all potential energy. And then I want to know at equilibrium, how fast is it moving? Well, at equilibrium, the force is 0. So at equilibrium, that's the point where there's no potential energy, and it's all going to be kinetic. And we know then that potential energy is 1/2 kx squared when we're in a spring, and kinetic energy is 1/2 mv squared. So if I want to find the velocity, it's just a matter of the halves cancel out. It's just a matter of finding the square root of kx squared over m. Great. Well, we know m. Do we know x? Well, we do, because the x at the amplitude, when I'm at the maximum amplitude, the x is 0.13 meters. But what about k? What are we going to do with k? Well, I guess it wasn't as easy as we thought, but we can do this, right? We can say that we know that the period of a spring is 2 pi square root of m over k, right? And I can just do some fancy algebra. I'm going to square both sides. And then I'm just going to do some rearranging to find k. So k is 4 pi squared m over t squared, but we know that t is the same as 1 over f, so k equals 4 pi squared m f squared. So how do I solve this problem? I would plug in for k first, plug in these numbers to get k, and then I plug in k into here in the amplitude to find the velocity. When you do all that, I'll give you a chance to check that for yourself. And when you do all that, what you should find is, you should find that at the center you are going 2.45 meters per second. So I'll give you a chance to try that. The rest of the class is yours to be working on your syllabus. You should have plenty to do because you've got 2 sections of the syllabus you can do now. You can do all about this. What is it? Let me get the syllabus here. You can do all of the questions about Hooke's law on springs, and you can do all the questions about energy of springs. So you've got plenty to be working on, so please be using your time wisely. If you have questions, please feel free to email me or send me a school